Okay, so we're going to look at what happens with the graph of e to the x. So the black line there, that's our graph of e to the x. It's an exponential function. You might remember it had an asymptote at y equals 0, just like all exponential functions. Now the crazy thing, and this only happens with e to the x, a crazy thing happens with the derivative. That's quite beautiful. So here we have this number e, which is 2.718281828, and it goes on forever, just like pi goes on forever, with no apparent pattern, even though it's easy to memorize the first 9 digits, because there's like the 18281828 thing that repeats itself a little bit. But then after that it goes crazy. So we got this crazy number, and when we do the derivative and we trace out all these different slopes, what do you notice? It's the same thing. It's one of the easiest and sometimes more confusing derivatives because it doesn't change. So when we go back to our notes here, the derivative of e to the x is e to the x. It doesn't change. Except when you have a chain rule built into it, then you have to do all that kind of stuff. So we'll get to that. But to start with, it is the easiest derivative because the derivative of e to the x is itself. So if you had to find the derivative of 5e to the x, yes, feels good. No problems so far. If you had to work backwards with an e to the x, well, the e to the x part would be the same. What would the working backwards be for the first one? 3x to the 5. Perfect. And then you could have any number at the end. So we have plus c. No problems. So what we're going to try to do now is if we think back to that graph, and I was able to drag my point right there, at 0, 1, what is the equation of that tangent line? Well, what do we need for an equation of a tangent line? We need a slope and a point. We get our point because it's given to us. I'm going to just do a quick sketch of the graph already. Here's e to the x increasing like this. Here's the point 0, 1. And here in red, my tangent line, not necessarily drawn to scale. That's what we're trying to find, the equation of that tangent line. Well, we know the point is 0, 1. In order to find the slope, we're going to need to do the derivative. So you do have to show the work that you found the derivative, even though it's the same, because this is the process for finding any tangent line, because that derivative gives us all of the slopes of all of the tangent lines. If we wanted to find the tangent line at 0, 1, that's when our x value is 0. And if you plug in 0 into this equation, we get e to the 0, and anything to the power of 0 is equal to 1. So we find out that a slope of our line is equal to 1. Again, you can go directly to the answer, y equals mx plus b. How do I know b already? Because that's the point we're finding. We've already been given that the y-intercept is 0, 1. So you could just write y equals x plus 1 automatically. You wouldn't have to figure it out. If the point they gave you wasn't 0, 1 or wasn't a y-intercept, then you'd have to plug in a value for x and a value for y and solve for that value of b. But not too bad. So what happens when you have other powers other than e to the x? Like what happens if you have 2 to the x or y equals 3 to the x? Well, it ends up being very similar. It stays the same, but you have to multiply by the natural log of b or whatever number it is. So what does this look like here? If we want to find dy dx of this, it's going to be the same, but then you have to multiply by the natural log of 3. And the derivative here will be 10x. A little proof of that. See, how could I do this as a little proof? I'll think of a good way of why this works out. Got an idea, but I might flounder a bit, so I'll make as a base of e, the natural log in the exponent. Okay, we'll come back to that. Now we're going to look at natural log.